A singly linked list is one of the most fundamental and widely used dynamic data structures in computer science, providing an efficient and flexible way of storing and manipulating collections of data. Unlike arrays, which store elements in contiguous memory locations, a singly linked list stores data in individual nodes scattered throughout memory, where each node consists of two parts: the data field and a pointer, or link, to the next node in the sequence. This structural organization allows the list to grow and shrink dynamically at runtime without the need for pre-allocating memory or shifting elements, making linked lists more versatile for applications that involve frequent insertions and deletions. A singly linked list begins with a special pointer called the head, which stores the address of the first node, and the last node in the list points to null, indicating the end of the structure. The dynamic nature of linked lists makes them ideal for implementing stacks, queues, symbol tables, adjacency lists in graph representations, and numerous memory-efficient algorithms. Since elements in a linked list are not indexed like arrays, accessing an element requires starting from the head and traversing forward node by node until the target is reached, which gives singly linked lists a linear time complexity for searching, although this makes them less efficient than arrays for random access. Linked lists offer constant time insertion and deletion at the beginning of the list because only pointer adjustments are needed rather than shifting many elements, as is required in arrays. Inserting or deleting a node in the middle of the list is also efficient, provided the previous node is known, since it involves reassigning one or two pointers. This strong advantage in modification operations gives singly linked lists a significant role in scenarios involving dynamic data handling. A singly linked list node is typically created using dynamic memory allocation in C, such as using the malloc function to allocate memory for the node structure during runtime. Each time a new element is added, a new node is allocated, filled with data, and the pointer of the previous node is modified to connect to the newly created node. Variants of singly linked lists include circular linked lists, where the last node points back to the head instead of null, forming a continuous loop that is useful in applications such as task scheduling in operating systems and buffering in streaming applications. Although their fundamental structure is simple, singly linked lists require careful pointer management because improper handling may lead to issues such as memory leaks, dangling pointers, or loss of access to nodes. For example, if a node is deleted without saving a reference to the next node, the rest of the list can be lost permanently, demonstrating the importance of proper pointer sequencing. Singly linked lists also form the foundation of more complex structures like doubly linked lists, where nodes include a pointer to the previous element, and linked list variants used in advanced algorithms such as skip lists. They are particularly useful when memory is fragmented, as nodes can be stored in the scattered free spaces of the heap. Unlike arrays which require continuous memory blocks, the operations of a singly linked list include creation, traversal, insertion, deletion, searching, and destruction. Traversal is performed by advancing a temporary pointer from the head through each node until null is reached. Insertion can occur at the beginning, end, or a specific position. Inserting at the beginning simply requires creating a new node, pointing it to the current head, and updating the head pointer, which is extremely efficient. Inserting at the end requires traversal to the last node and updating its next pointer. Inserting at a specific position requires identifying the previous node and adjusting pointers accordingly. Deletion follows similar logic. Deleting the first node involves pointing the head to the next node, while deleting the last or a middle node requires updating the previous node's pointer to skip the node to be removed. After deletion, the node's memory should be freed to avoid memory leaks. Searching in a singly linked list is performed linearly by comparing each node's data with the target value, although the time complexity is O(n). This sequential search is expected, given the list's non-contiguous memory structure. Singly linked lists also have practical applications in implementing polynomial operations, big integer arithmetic, sparse matrices, and real-time event handling systems. For example, polynomials with unequal degrees can be efficiently represented using linked lists, where each node represents a term with coefficient and exponent. Sparse matrices, which contain mostly zero values, use linked lists to store only non-zero entries, significantly reducing memory usage. Linked lists are also common in compilers, where symbol tables and dynamic structures required during parsing are implemented using nodes and pointers. In operating systems, process control blocks, device buffers, and scheduling queues often use linked lists due to their dynamic nature. Despite many advantages, singly linked lists have limitations. Their major drawback is the inability to access elements directly by index, resulting in slower searching compared to arrays. Linked lists also use more memory per element because each node stores an additional pointer. Furthermore, frequent memory allocation and delocation may increase overhead and fragmentation in the heap. However, in applications where flexibility and dynamic sizing are more important than speed of access, singly linked lists remain an essential and preferred data structure. They balance memory efficiency, dynamic growth capability, and fast insertion and deletion, making them ideal for situations where data changes frequently. The simplicity of their structure leads to widespread use in educational environments, where they serve as an excellent introduction to pointers, dynamic memory, and advanced data structures. Overall, the singly linked list continues to be one of the foundational concepts in computer science, offering both practical utility and important theoretical insights into memory management, pointer manipulation, and data organization.